Hi students, welcome back to the session on free vibration. So in this video, we're going to say about the basic elements of vibrating system and the types of vibrations we're going to see. So the basic elements of vibrating system involves three major elements, that is a mass, spring and a damper. If you take the mass stores the kinetic energy, whereas the spring it stores the potential energy and a damper dissipates the energy. So the mass is the rigid body whose acceleration x double dot according to Newton's law is proportional to the resultant force of all the forces acting on the mass. So F is equals to mx double dot. So if that mass is the one which gives the initial for which we're going to give the initial excitation due to which other two elements will be acting. So whenever the mass is pulled downwards, if you take this as the longitudinal vibration, when you go to pull the mass downwards, the spring and the damper will try to restore the position of the mass into equilibrium position. So the spring and damper always opposes the motion of the swing. Whereas spring will keep the object in a to and fro motion unless it gets completely damped down. So the changes, when you go for spring, the change in the length of the spring is proportional to the force acting along its length. So I'm going to take F is equals to K into X minus U. So normally you're going to take as U as 0. So K F is equals to K into X. X is the displacement, how much you're going to give for the mass. So the ideal spring is considered to have no mass. So spring will be having no mass. We're going to consider if the spring is having a mass, then again it will be having effect on the equation of the motion. So the force acting on one end is equal to the opposite to the force acting on the other end. So if I take the other ends, so if the force is acting over this downwards, this force will be acting upwards and it will be equal. The constant of proportionality K is the spring constant or a stiffness. The K is nothing but the stiffness of a spring. So it will be varying based on the spring you're going to use for the motion. So when you go for the damper, so damper, normally the viscous dampers will be considered for the vibration analysis. So that is very simple. The differential equation will be very simple for calculation. That's why normally you're going to consider the viscous damping as the example for that. So in the viscous damping, the period of the applied force is proportional to the relative velocity of its connection point. So always the damping force will be given by F is equal to C x dot. So x dot is nothing but the velocity, where C will be the damping coefficient. The characteristics parameters of damper is nothing but the damping coefficient. The ideal damper is considered to have no mass. Thus, the force on the end is equal and opposite to the other end forces. This is very similar to the spring. So you can see over here, the spring has a displacement x, the damper has a velocity x dot, and the mass will have a inertia, that is x double dot acceleration. So this is the basic schematic representation of a spring mass damper system. If you take the same image over there, so as I said, mass will be going to store the kinetic energy, which will be converted into potential energy. Similarly, the spring will be having a potential energy, which will be converted into potential energy during the motion, and the damper will be just absorbing the energy, and it cannot support the load of the mass. So if you take the forces, so M will be acting downwards, that is mx double dot, there will be kx and cx dot. So mx, always the inertia for most will be acting away from the acceleration. So I'm going to get as mx double dot plus cx dot plus kx equals to 0. So that is the three forces acting on the body. So this is the generalized equation of a vibrating system, which is a damped one. So coming to types of vibration. So normally the types of vibration based on one, it is based on the excitation. The second one based on the absorption of energy. Third one, it is based on the input, and fourth one by knowing the values. So if you take the first one, the vibration, free vibration and forced vibration. So the free vibration, if a system after an initial disturbance is left to vibrate on its own, the ensuing vibration is known as free vibration. So just if you take a pendulum, what you want to do in a pendulum is just you want to take the ball and you want to take to a particular height and you want to drop off. So in between you won't apply any force on the ball. So the motion will be continuously going for to and fro, and it's going to stop at a particular time. So this type of motion is called as free vibrating system. So there's no external force acting on the system. The oscillation of a simple pendulum is an example for a free vibration. If I go to take the forced vibration, if a system is subjected to an external force, so often a repeating type of forces is resulting in a vibration is known as forced vibration. The oscillation that arises in machines such as diesel engines is an example. So there will be a continuous run of the pistons. So what will happen? It's going to create a vibration in the engine. So that engine will be continuously vibrating only because of the external force. So that extra force is going to stop means the vibration automatically reduces for the system. The next type of is based on the energy absorption. So damped and undamped vibration. So if no energy is lost or dissipated in a friction or any other resistance during the oscillation, then that vibration is known as the undamped vibration. So in this case, there will be only a spring and a mass system will be there. So damper will be neglected. If the energy is lost, so then it is called as undamped vibration. So normally there will be combination of this forced undamped vibration, forced damped vibration, free damped vibration, free undamped vibration. So both the things you're going to study in the syllabus. So you're going to study undamped vibration as well as damped vibrations. So coming to linear and non-linear, if the basic components of a vibrating system, that is spring, mass and damper, behaves in a linear way, then the resulting vibrating will be a linear vibration. If any of the basic components behaves non-linearly, means there will be fluctuations continuously, then it will be a non-linear. So the vibration is called as non-linear vibration. So what are the types of free vibration you're going to get? So according to the motion of the system with respect to the axis, so there are three motions you're going to study, that is longitudinal vibration, transverse vibration and torsional vibration. So the longitudinal vibration is nothing but when I want to give the moment, the vibration takes place along with the axis. You can see over there, if B is the equilibrium position, it goes to A and it comes back to C. It is acting along with the axis. So this kind of vibration is called as longitudinal vibration. When you go for the second one, that is transverse vibration, it goes for a to and fro motion perpendicular to the axis. If we're going to give the motion perpendicular axis, that type of motion is called as a transverse vibration. And torsional is nothing but the rotation. When you go for a twisting, twist out and twist in is called as a torsional vibrations. So coming to simple harmonic motion. So simple harmonic motion is a special type of periodic motion where the restoring force on a moving object is directly proportional to R and opposite of the object's displacement vector. So let us consider a Scorchak mechanism, so also called as slotted link mechanism, which is nothing but a reciprocating motion mechanism, converting the linear motion of a slider into rotational motion or vice versa. So the position of the rotating part is directly coupled to a slide link arc, which slot that engages the pin and rotating. If you see this is a slotted rod. So if the position is at 0, that is angle 0, so it will be at the position O. So when it goes to move, go for an angle theta, so it goes go for a movement, so that is x displacement is given, so the movement has been taken over here. So theta is nothing but omega into t, that omega is nothing but angular velocity and t is the time taken over there. So equation of motion, the displacement can given as a x is equals to a sine omega t. A is nothing but the amplitude of the vibration, sine omega is nothing but angular velocity, t will be the time taken. So when it goes for complete rotation, the mass will be moving, as k is the stiffness, the mass will be moving and that will be recorded into a sinusoidal way. You can see the timing 0 to pi, that is 0, pi, 2 pi, 3 pi, again it will go for pi. So that is we can say as 4 pi also you can say that. So that is the complete motion I am going to get. So when you go for that, the displacement is given by a sine theta. Theta is nothing but omega into t. So a sine omega t are going to get. So when you're going to differentiate that, the velocity becomes x dot equals to dx by dt. That is omega a cos omega t. So differentiation of sine is nothing but cos omega t. When I'm going to differentiate again acceleration. So acceleration, that is x double dot, that is nothing but d square x by dt square. So I'm going to get as minus omega square a cos integration will be minus sine omega t. So a sine omega t is nothing but x. So I'm going to substitute that x double dot as minus omega square into x. If I take omega square into x this side, it becomes x double dot plus omega square plus x equals to 0. If you take the example of a elements, so we're going to get elements, that is mx double dot plus cx dot plus kx equals to 0. If I leave the damping equation over here, so it becomes mx double dot plus kx equals to 0. If I divide the whole equation by m, I'm going to get as x double dot plus k by m into x equals to 0. So that is very similar to the simple harmonic motion equation. So where I'm going to get as, so x double dot plus omega square into x equals to 0. So omega square is nothing but k by m. So in a simple harmonic motion, always the acceleration will be directly proportional to the displacement. So that will be having a opposite direction. So next video, we're going to see about the other topics of the free vibration.